combinations that we've seen so far. Hopefully you won't chase me out with pitchforks, but we'll find out. I am a second-year PhD student at the University of Edinburgh. My advisor is Mike O'Boyle. He's on the paper here. Mikhail helped a bit as well. So first, I think I should mention I do not consider myself to be a Haskell expert. That doesn't mean that I don't want to be one. It means that that I'm just not. I'm trying, but I'm not there yet. And I'm trying to get more involved in this community. It's been really difficult in this last year for obvious reasons. And I should have been much more involved much earlier for this project. And that actually my not being super involved has come back to bite me. And I'm gonna kind of circle back to that later in this talk, and we'll hear more about that. And next I wanna mention that this is not the paper that I originally wanted to write. The paper that I originally wanted to write, hold on, there, looked a little bit more like this. I wanted to write a paper about optimizing GHC's inliner with machine learning. And in the process of trying to do that, I very quickly discovered that we don't have an adequate benchmark suite for GHC, which is very problematic. We have NoFib, the canonical benchmark suite that came out in about 1993. And now all of its programs run within about a fraction of a second. And it's widely acknowledged that it needs a huge overhaul or a replacement. So that means, bummer, I don't really have any good tools to measure my changes with on GHC, which is kind of a huge problem, which means before I can do what I actually want to do, I have to build a benchmark suite. And building benchmarks is not a small task in itself. And unfortunately, it's also probably a thankless task outside of the GHC community. And there's also a good chance that it's not going to be publishable. So what I wanted to do was take that step and pull something possibly publishable out of it as some sort of like a prize for my agony. And the motivation for that thing that I pulled out can be described in a meme that I found on Twitter. And I hear that memes are better when somebody explains them, so let's just jump in with that. This is from some Marvel and/or DC Comics movie, and we have Kirsten Dunst and we have Jake Gyllenhaal, and Kirsten says, "Tell me the truth, I'm ready to hear it." And Jake responds, "Most of the time, you don't need deep learning. You won't even need machine learning." So this work that I'm sharing with you right now is about that. It's about justifying the use of machine learning with data, because I think that's something that somebody needs to make a statement about. All right, so here's my revised to-do list. I need to build a benchmark suite, and then I need to show some room for improvement and that there's some worthwhile speed up to be gained. And I also need to show that machine learning is probably advisable. And then I can do my thing. So first, to build the benchmark suite, I decided we want to somehow take packages from Stackage, because it seems like they will be representative of the real world. So you all probably know what Stackage is, but I'm going to try and awkwardly explain. Stackage is an open source collection of Haskell packages that are bundled into these things called nightly builds, and they're all guaranteed to build with each other for that specific Stackage nightly build. So my benchmark builder is basically a set of Python scripts. They take a list of packages that you give it, they take a given GHC that you give it, and then they download and build the packages, and then they try to run the tests, and then they write the test times to CSVs. Additionally, I had some R code for visualizing the timing data. Now, there's a slight problem with this. About 34% of the packages on Stackage use this thing called QuickCheck, which is a library that creates randomly created test cases, which means that when I run my times, they're non-deterministic and I get a whole lot of noise. Fortunately, you can just go into QuickCheck and you can set the random seeds such that it's the same thing every time. And then you can go back into the benchmark builder and you can hack it such that all of the projects will now rely on my hacked QuickCheck instead of regular QuickCheck, which is non-deterministic. So I chose one single Stackage nightly build to look at, and I downloaded it. That build had 2,218 packages. Among those, 1,420 had runnable tests. That is too many packages for training or analysis. But that set, I think, would be good for testing afterwards if I do make changes to GHC that I decide that I want to keep. Like, hey, let's take this and run it over all of Stackage and see whether it's good or bad. I think that sounds like a good idea. So, selecting my benchmarks. I was mostly looking for programs where GHC was inlining poorly. Because again, my objective is I want to demonstrate room for improvement. So while I was kind of blindly poking around package, looking for good examples to unearth evidence for room for improvement, I ran upon these things called inline pragmas, and I had a hunch to look at those. And I'm going to crudely explain what inline pragmas are to you, even though most of you, again, probably know what they are. They're you can manually, as a developer, you can insert an inline pragma underneath the declaration of a function that will tell GHC, hey, try really hard to inline this. And GHC will see the pragma and go, okay, I'm going to try really hard to inline this thing unless it breaks everything, in which case I won't do it. Now, about these inline pragmas, about 14% of Stackage, all the packages on Stackage have them, which seemed like kind of a high number to me. And so I thought, okay, so does this mean that these developers who made these 14% of packages, maybe they know something the GHC doesn't? Maybe we should look at that. So I came up on this one program just early on and did a manual check. It had one inline pragma in it. This program was called Yampa, one inline pragma. When you take it out and compare it versus when it's in, it has about a 25% speed up. That seemed promising. So I take my Stackage packages and I filter them further. I want to look for packages that have inline pragmas. That leaves me with about 236 packages with inline pragmas and runnable tests. So among those, I further subselected because it takes me time to run these experiments. And I chose 10 packages, largely because they ran for more than 4 seconds each. Some of them significantly more than 4 seconds each. And it would be easier for me to see, like, if I make changes and there might be a more dramatic improvement versus if they run for less than 1 second. Okay. Next, I had to modify GHC's inliner. And I need to do modifications such that we can, plausibly observe some execution time changes. So if you notice, I've got a nice big cursor. These yellow numbers right here, they're kind of sprinkled all throughout the inliner. These are, I'll circle them. These are actually hand-coded magic numbers, and they're thresholds that are kind of like embedded inside this inlining decision. And we can actually just look at one or two here. Here's one. It says, apply a discount of 10 because the result replaces the call. So we count 10 for the function itself. And then that one, there's a plus sign under here. That one is added to it 10 times length actual arg discounts. And this 10 here says discount of 10 for each arg supplied because the result replaces the call. So this is not the entirety of the flags that I replaced, but this is some of them here. There were others. And I can show you in a table the ones that I did choose to change. They're all based on language constructs themselves. And I should note that these last two down here actually kind of came in with GHC by default. And I just thought, why not? I'll throw those in and randomize them just to see what happens. The generation of the new thresholds. Oh, right. Wait, hold on. I didn't explain this well. I took these magic numbers out and I turned them into dynamic flags. There, that should make more sense. Such that for each one of these magic numbers, we could use a dynamic flag and set it at compile time from some randomly generated distribution, and we can replace whatever default was in there with something else and see what happens. I hope that makes sense. Okay, the generation of the new thresholds came from a normal distribution. The mean was the original value of the threshold. The standard deviation was about 40% of that default value. Okay, why? So it's reasonable to assume that the space of possible inlining decisions is enormous. We can also assume that good solutions are they're clustered together, likely, and probably sparse within this space. And I'm also assuming that GHC probably makes a fairly good attempt at coming up with a solution as it is. So if we use a normal distribution, we can kind of stay near GHC's value and only deviate from it perhaps drastically a little bit on a few values and just kind of wobble around a little bit. The experimental setup itself, to calculate the baseline, I removed the inline pragmas from the packages, timed each one of them 10 times. And then I calculated each project's average. Then we ran 3 experiments. Experiment number 1. We took the pragmas out of the packages, timed them, got their averages, and then compared their times to the baseline. So for the fun here, you can see how many pragmas each of the projects had. We have a minimum of 2, to maximum of 520, and half of them were less than 10, but some of them just kind of went all out. Here's 16, 57, 88. So the question is, do the pragmas really help? The answer is not really. Actually, they make hardly any difference at all for most programs, except this one, Poly, where it makes an enormous difference, and there's about a 62% speed up. That one had, let's see if I remember, Poly had 57 pragmas, not too shabby, but again, there are more that had like non-empty containers had 520. And here, yeah?
Is polysemi the effect library?
I don't think so, no.
Okay.
I don't think I have the descriptions. Actually, maybe I do. Haskel library for univariate and multivariate polynomials backed by vector.
Okay,
yeah.
Thank you.
I did check that that package was still being maintained, and it seems to be in use. So it seems to be substantial. But again, I'm not an expert. Okay, so just looking at pragmas versus no pragmas, just that one single poly basically drives up the geometric mean speed up to about 4.79%, for whatever that means. Experiment number 2. We're going to randomize GHC's magic numbers. We're going to compile it against programs without the pragmas in them. And then we're going to compare it to the baseline. We did that for 70 configurations. Why? Long story short, that was the time that I had. You can ask me about that later. Okay, so the slide that we're looking at now is among that data set of those different configurations, we're going to take the best case configuration for each project. So assuming that we had the best configuration for each project and we magically knew how to arrive upon that, what's the geometric mean speed up that we get? It's 5.69%. So most of these packages managed to find something that was better than GHC, like significantly better than GHC, maybe 3% or above. This one is about 18%. Poly was nowhere near as close as the pragmas, at about 13%. Again, not bad. Okay, so if we look at this data set particularly, I did a histogram of all of the projects' speedups, individual speedups together, because with this data set, we can better see what the effects of randomization of GHC is without the pragma coercion. So it turns out that about 63% of these configurations were slower than GHC. There were a few of them that were just horrifically bad, like 60% worse. But about 37% of them were faster. And that was a little more positive than I had anticipated, that it seemed a little bit more easy to find speedups than I thought it would be. Experiment number 3, we randomized GHC's magic numbers. We compiled the programs with the pragmas in them, and then we compare it to the baseline for 70 configurations. If we look at the best case scenario for each project into that, we get a geometric mean speed up of about 12.09%. So if we look at poly again, before it was 60-something% with pragmas. If we do pragmas plus randomization, that brings it to 77.24% in the best case. And then there are also a number of significant speed ups. The only one that I think that is less than 3% is this one right here with 1.7, but the rest are 3, 5, 4, 9, 20, 21. Okay. Combining that all together, if we look at the best average time from each project for any run, such that we can put together some sort of like an oracle, like among the data set that we've seen so far, what would be the best solution for each package. We can nudge that up a little bit to a 12.61% geometric mean speed up. So presumably there's one or two projects that did a little bit better with just pure randomization without pragmas. And then the rest I think largely came from the data set with pragmas. I should note here that the geometric mean speed up that you see right here, the 12.61%, is slightly different from the number that I reported in the abstract, because the abstract came from a paper that I submitted to the Haskel Symposium. And since then, I did discover a slight reporting bug, but the numbers are like a little tiny bit different, but the spirit is still very much the same. All right, so the same question that you would ask at this point is, can we approach that 12.61% speed up with a single best configuration? And to answer that question, we need to consider the data set that does not have pragmas in it, because we can't take those pragmas and suck them back up into GHC and then somehow apply that knowledge to other programs. We really just have to go by randomization alone, such that we can only modify GHC's numbers. So only looking at that data, the answer is no. If we look at the single best geometric mean speed up, one configuration across all projects, we get a geometric mean speed up of 3.82%. There are some significant speed ups in some of these projects. I don't see any significant slowdowns. So overall, it seems like it's not too bad, but it's really nowhere near this oracle of perfect decisions that we've seen might be possible before. So here's the more interesting thing. This is a set of histograms from all 140 randomly generated configurations. We take each value of each flag for each configuration, we put them into histograms, and they should look more or less normal, modulo some spikes from perhaps binning, but they look more or less normal. So basically nothing up my sleeve, and my tool is working. If we take the top 10 runs for each package and plot histograms of the threshold values for each of those projects for each of the top 10 runs, our distributions start looking a lot less normal. So they actually start looking like they're maybe, in some cases, uniform or maybe multimodal. There are two possible explanations that I would propose. One is that the values don't really matter all that much. Like maybe these thresholds just don't matter all that much, and it doesn't matter what we choose. Or two, each of these packages prefer different values. So another way to visualize this, here's another graph where we take the single best flag from, we take the best configuration for each package, and then we do a box plot of each of those flags. So each box plot has 10 preferred values. We can see that there are a few of these here that seem to have strong preferences, which is good. We could put that perhaps directly back into the code. However, there are these here that have quite widespreads, which suggests that there may not be a single best value for these flags. So the thing is that GHC developers, they've spent quite a lot of time tweaking these thresholds. And the GHC codebase itself is really littered with a lot of nice detailed comments that say that when I change this threshold, something in nofib blows up or does really well or does really poorly. And these notes are all over the place. But it may have been the case that trying to find the single best value for each of these thresholds might have been a futile task. So the conclusions that I draw according to my data is that we observed a possible speed up of 12.61% within a relatively few data points, really. It was between 140 different configurations. And we can't really get to that speed up just by tweaking the existing code that we have. So in the context of this information, a rewrite of the inliner would be advised. And I would further recommend machine learning so that, well, because it's an extremely complicated task. And machine learning can probably recognize patterns that we can't. There were some other conclusions that are not entirely related to the research that I wanted to add here. So as I mentioned, I submitted this to the Haskel Symposium recently. They didn't like it. Well, actually they did. So the reviewers, they were very positive about it. But they didn't like the way that we explained it, and they didn't like the packages that we chose. And I accept full responsibility for this because I didn't reach out sooner. And one of the biggest problems really was that we submitted it to the wrong category. I submitted it as a research experience, which is 6 pages, and it probably should have just been a regular entry at 10 or 12 pages, which would have given us a lot more room to explain. And then also talking to people more, I could have chosen better packages, and I think I could have, possibly avoided that rejection. So, additionally, I should mention, I had a nasty bug that I was fighting with up until the very last week. But I mean, regardless of that, if I had still spoken to people, then they could have helped me, even though my data was a little bit skewed. Because it turns out that I think the bug probably wasn't even my fault. I did find a workaround for it. But the point that I want to make is that even if you think that your stuff is broken, you should still talk to people. You should talk to a lot of people. You should talk to them a lot, and you should talk to them early. Okay, that's really the end of my talk. If you have any questions, I think this is the time that you should ask them.
All right, thank you, Celeste.
Uh-huh.
We're going to have the questions in